Okay, so welcome everyone. We're very lucky to have Prem Kumar from Swansea, who's going to give us a talk on islands and page curves for evaporating black holes. Take it away.
Thanks very much. Thanks, Nathan, for the invite as well. So I'm very happy to give this talk. Of course, like everybody else, I wish I was at Cape Town, but then such are the circumstances. So, this is a talk on work that I recently did with my collaborator Tim Hollowood at Swansea, and so I would encourage people to actually ask questions, because as I was preparing this talk, I realized that it has actually come out a bit longer than I wanted it to be. So if people would like to clarifications at any point or would like me to speed up, please do so without any hesitation. So the main motivation for this work is essentially the topic of the information loss paradox in black holes. And what we wanted to understand is what happens when we actually throw something into a black hole, and how does the page time associated to the black hole change, and when is the information of what's thrown in, when is it recovered? And of course, can we calculate answers to these kinds of questions within a concrete model? So that's the general motivation. It's a very simple set of questions. And of course, these are motivated by the current exciting developments in the resolution of the black hole information loss paradox, initially enunciated by Hawking, and in which the basic idea is that the entropy contained in Hawking radiation, which is emitted by a black hole, given that the radiation is thermal, it's something that increases linearly with time. And this formulation of the information loss paradox is made most crystal clear by the observation due to Page that if one computes the von Neumann entropy in the Hawking radiation, because the Hawking radiation modes are entangled with degrees of freedom inside or behind the horizon, one computes the von Neumann entropy of the Hawking radiation, assuming that, for example, the initial state of the system was a pure quantum state. In that case, what one would expect is that this von Neumann entropy in Hawking radiation should increase potentially linearly with time at long times. But then at some time scale, which we now call the Page time, we expect this entropy this increase to turn around, so that the entropy eventually goes back to zero when all the degrees of freedom inside the black hole have evaporated. So the idea is that the von Neumann entropy of a pure quantum state is zero, and therefore the entropy in the Hawking radiation, which starts off from zero, eventually must also end up being zero. So this is probably the most precise way to formulate the conflict between the semiclassical calculation performed by Hawking, which was valid in the semiclassical approximation, and the expectations based on unitarity in quantum mechanics. And the basic point here is that this is a glaring discrepancy between Hawking's result and what one would expect. And this discrepancy is really an order 1/gn effect. So it's not a small effect, it's a large effect. And so in this sense, the paradox is actually accentuated. So the page time, of course, is the time scale at which roughly half the number of bits of information have been emitted, and so the entropy of the black hole has roughly reduced by a factor of a half. So this is a statement. This page curve is something that we would expect to see the turnaround for an old black hole, and really the question is to reconcile the expectations for an old black hole from quantum mechanics versus Hawking's result for the Hawking radiation. Okay, so the resolution for this discrepancy has recently been proposed, and it's quite a remarkable development. And the first, perhaps remarkable or surprising aspect of this is that the potential conflict is actually resolved in semiclassical gravity. So there is no need for us to look for a full-blown quantum description of gravity. In fact, if we have a consistent framework where we can do semiclassical calculations in gravity, we should be able to see its resolution. And the main point of this resolution is done by these papers progressively by all these authors here. The main point is that when one does the von Neumann entropy calculation, which is the entanglement entropy calculation for Hawking radiation, one uses the famous replica method. And what one finds is when using the replica method, one obtains new classical or semi-classical saddle points, one of which is this wormhole saddle point, which dominates at late times and is responsible for actually deviating from the Hawking's prediction and yielding the expected page curve. So these replica wormhole saddle points are also in one-to-one correspondence with things called quantum extremal surfaces, which are very closely related to the idea of the Ryu-Takanagi minimal surfaces in holography. So the replica wormhole saddle is closely related to this idea of a quantum extremal surface, which I will briefly describe. But this quantum extremal surface is a contribution to the von Neumann entropy of entanglement. And what these quantum extremal surfaces do is they identify islands behind the horizon. And roughly speaking, when one does the calculation of the von Neumann entropy, one, roughly speaking, essentially deducts the contributions from these islands that appear behind the horizon, because actually this island behind the horizon in an old black hole is in fact contained in the late Hawking radiation, and therefore you need to actually take its contribution away when you are computing the total entropy. That's roughly the idea. Okay, if there are any questions at this stage, please feel free to raise your hands or unmute and ask. Okay, so this is the outline of the talk. I have kind of 4 distinct sections. The first part is going to be a review of the basic setup within JT gravity or two-dimensional gravity, which is the framework where we are going to be doing the calculations described. And then I'm going to be talking about setting up a shockwave within the framework of JT gravity, which means throwing in something into this black hole. And then we will find that there are ways in which, or there are regimes in which the ensuing dynamics becomes tractable. And in particular, we will describe certain limits, which are semi-classical high temperature limits in which we can track the evolution throughout, but in a fairly simple way. And at the end, what we want to understand is these quantum extremal surfaces and associated islands and the page curves that follow during the evolution of this black hole. So we have a black hole which is excited by a shock wave thrown in, and then the system relaxes, and we want to understand the ensuing dynamics. So that is that's the outline of the talk.
I have a quick question. That's all right.
Yes.
So you say there's this island behind the horizon. Is that in the same kind of vein as something like ER equals EPR? You're saying that there's a kind of region outside the black hole that's somehow still entangled with something behind the horizon?
Exactly. So that's in fact, that is exactly the point, that it's a manifestation of this ER equals EPR in a very precise sense, in the geometric sense that the region behind the horizon in these islands actually becomes connected to the Hawking radiation physically through these replica wormholes. And so that is the manifestation of the ER equals EPR, indeed.
Okay. Cool, thanks.
I'm sorry, could you just go back one slide? I missed your definition of the island.
Yeah, so I didn't. So the quantum extremal surfaces actually define certain regions behind so they have an associated causal development, and from that you can basically read off the island. So given a quantum extremal surface, you can identify an island region, and that island region is basically a region that you are essentially double counting when you're doing the Hawking calculation. And that region is actually entangled is contained within the Hawking radiation that you've got in the old black hole.
Is this what would be is this related to something like a RT surface?
Yes, so the quantum extremal surface is exactly an RT surface. In fact, that is how the quantum extremal surface was found. I think first the calculations were originally set up in a holographic framework where the example is you have a you have a black hole which is in the there is a CFT, two-dimensional CFT interacting with a black hole, and there is a holographic description of this two-dimensional CFT, which is an ADS3, and then one looks at these root Takanagi surfaces in this ADS3 geometry, which is actually happens to be dual to what we would call a boundary conformal field theory. And so these root Takanagi surfaces are indeed related directly to the quantum extremal surfaces. The point is that these quantum extremal surfaces can, however, be spoken of independent of holography, but there is a chain of arguments that connects the two.
Okay, thank you.
Okay, so the setup is this so-called JT gravity, which is 2D gravity with a dilaton, and it's JT gravity coupled to a matter bath. So the essential physics is captured within the framework of 2D gravity plus matter system, where this matter is what will be giving rise to the Hawking radiation, and we will take this matter to be a CFT. And this CFT is basically formulated in this background. So it doesn't back react on the geometry aside from purely semiclassical back reaction. So if there's a non-zero stress tensor, it can feed into the background, but there are no loops of the matter field introduced. So the back reaction of the matter is purely at the semiclassical level. So again, the framework is 2D gravity with CFT matter, which is propagating in the background. Okay, so the reason this framework is very attractive is because it's a natural way, it can naturally be embedded into a higher dimensional framework. And in fact, JT gravity plus the CFT bath or the JT gravity itself can be viewed as the S-wave sector of some higher dimensional theory. So you could have a black hole in some higher dimensional gravity theory. And if you have a near extremal black hole and view its near horizon limit and perform dimensional reduction over the compact modes, then you will effectively end up with something that looks like JT gravity. And this has been made precise by several people. I think Almehri Polchinski originally. And so the near extremal black holes are associated with nearly ADS2 geometries. And so we will see that JT gravity is associated to gravity in ADS2. So the basic action for JT gravity is that of metric coupled to a dilaton phi here. And on top of that, we have this matter sector, which is propagating in this background. Now, what is special, as I've kind of already alluded to, is that the equations of motion for this system, the dilaton equation of motion, it fixes, the dilaton acts as a Lagrange multiplier, basically fixing r equals -2, which means it's a constant negative curvature. And so this metric is always going to be locally ADS2. So we are talking about ADS2. And just to be very precise, on the Poincare patch, and it will kind of be important not in what follows for me to make the distinction between Poincare patch and other coordinates. So I'll make clear that Poincare patch, this is ADS2 Poincare patch. So I define x plus and x minus as tau plus and minus x. Tau is the tau will be defined as the Poincare time, and it plays a special role. The boundary of this space-time is at x tends to 0, or when x plus equals x minus. The dilaton, the equation of motion for the metric, then gives us the equation satisfied by the dilaton, which I write out explicitly again in Poincare patch. On the right-hand side, you see is of this equation, the stress tensor feeds into the dilaton. So the dilaton and its behavior is governed by the classical or semi-classical stress tensor for the CFT matter which is coupled to the system. Kind of important aside which I throw here is that the stress tensor which enters the equations here, semiclassical stress tensor, is covariant because the equations of motion have to be covariant, which is distinct from the normal ordered stress tensor. So I write T mu nu classical as the classical or unnormal ordered stress tensor, and the normal ordered stress tensor is usually the CFT stress tensor, which actually doesn't transform covariantly under coordinate transformations because it gets an inhomogeneous piece in 2 dimensions, which is associated to the Schwartzian. Okay, so in the CFT, in the vacuum state, we are thinking about first the CFT in the vacuum state and Poincare patch. The classical stress tensor vanishes, so does the normal ordered stress tensor in Poincare patch. And the general vacuum solution to these, to the background consists of the ADS2 metric for the background geometry, and for the dilaton takes this particular form. So you can see that this form of the dilaton, this is the most general form that solves the vacuum equations. And there are basically 1, 2, 3 constants here. Phi naught is an additive constant for the dilaton. And so 2 phi r here is an additional constant which basically fixes the asymptotic value of the dilaton near the boundary. And pi square over beta square, of course, well, the reason I write this as 1 over beta square is basically it tells us whether there is a non-trivial energy associated to this background. In particular, whenever beta inverse is non-zero, there is a non-zero ADM mass associated to this background, and we would view this as a black hole. So the only non-trivial object here, as you can see, is the dilaton. Hopefully that's clear. The dilaton at the boundary diverges. Phi goes to infinity when x plus goes to x minus. And the singularity in this geometry is described by when the dilaton vanishes. Roughly speaking, the dilaton should be thought of as when one does the S-wave reduction, one can think of the dilaton as being controlling the volume of the compact dimensions. So when this volume is large, we expect things to be weakly coupled, the effective gravity to be weakly coupled. When the compact volume is small, we expect this to break down, and that's where we see the singularity. So the location of the singularity actually very much depends on phi naught, because you have to set this to 0 and you will see where. Okay, so non-zero beta inverse is a black hole, and black hole, as expected, is a solution to these equations of motion with vacuum on the right-hand side, so the stress tensor vanishes. So this is the description, the natural description of the black hole in terms of this black hole patch coordinates. So it's very much like going to Rindler coordinates. So we have here x plus minus going to tanh of y plus minus. And clearly, so y plus minus is going to be defined as t plus or minus y. And this t is what I will call the physical time, as opposed to Poincare time. Now, of course, these two are related just by a coordinate transformation. So we can see that when we define the black hole patch actually sits inside the Poincare patch, as one would expect. And t goes to infinity. Physical time in the black hole patch corresponds to some finite Poincare time. The horizon, the horizon of this black hole is at x minus equals beta over h. Okay, right. So that's the basic picture of the ADS2 black hole. Now, of course, these coordinates, they don't cover the black hole patch. This is not global coordinates. Now, you can extend the black hole to this, the ADS2 black hole to this double-sided picture that I've drawn here. And so what we are going to think about now is on top of this black hole, we are going to glue to both sides of this double-sided black hole, we are going to glue in Minkowski space. And the Minkowski space is going to provide us with the asymptopia. So the CFT, the matter fields, which will give rise effectively to the Hawking radiation eventually, the matter fields live on all of the space-time. They propagate on ADS2, but also in the flat space asymptopia. So this is a very simple model where we have basically taken a black hole and glued together, ADS2 black hole, glued together on either side of it, flat space. And this flat space will be viewed as the bath, okay, the CFT bath. And we will maintain this bath at some temperature beta inverse. And those will form the boundary conditions for the setup. And crucially, at the boundary between the ADS2 and the flat space bath, at the boundary between these, we put transparent boundary conditions or absorbent boundary conditions, which means the Hawking radiation from the black hole goes through, the flux of the Hawking radiation goes through into the bath, and the radiation from the bath goes into the black hole region. And in equilibrium, the incoming flux and the outgoing flux are equal. So in particular, Ty minus y minus equals Ty plus y plus at y equals 0, where y equals 0 is the boundary of the space. And the expectation values of both these is given by pi c over 12 beta squared, which is the usual thermal expectation value for the stress tensor. So these expectation values follow from just looking at the state of the CFT in this ADS2 geometry. So one starts with a Poincare patch stress tensor, the Poincare patch vacuum where the stress tensor has 0 expectation value. One does the coordinate transformation to the black hole patch, and in the black hole coordinates, the stress tensor expectation value just comes out to be the thermal expectation value, and that is dictated by the transformation of the stress tensor. In conformal field theory, when one does the conformal transformation, stress tensor transforms inhomogeneously by the Schwartzian, and that's the value of the Schwartzian. So both the incoming or left moving and right moving fluxes on either boundaries are balanced. And so we have equilibrium. So in JT gravity, there is no local degree of freedom. As we saw, the metric, the background is fixed, and of course the dilaton is also fixed. The only degree of freedom in JT gravity is the so-called boundary particle. So one can consider disturbances in this geometry that effectively correspond to redefinitions of the time coordinate t of the ADS2 boundary, and that's the only dynamical object in this theory. So, so whatever disturbances that we do, at the end of the day, geometry inside is always going to be ADS2. So we can always transform to the Poincare patch of ADS2. So the coordinate transformation then has an effect on the boundary of the geometry, and that's the only dynamical degree of freedom. Again, any questions, please interrupt. Okay, so in this geometry, one can then, as is generic whenever one has ADS type geometries, one can compute the boundary stress tensor, which also gives, in this case, the ADM mass. And the mass of this background is given precisely by the Schwartzian. So this degree of freedom associated with the boundary particle, which is associated to reparameterizations of the boundary time coordinate, has an associated function f. And the Schwartzian of this function, the Schwartzian derivative defined here, gives us basically the mass of the spacetime. Okay, so there is, in addition to this, there is a very nice and natural energy balance condition at this boundary. The rate of change of energy of the geometry, or of the black hole in this case, is given precisely by the difference between the incoming flux and the outgoing flux, which is of course conservation of energy. So in equilibrium, the incoming and outgoing fluxes are equal. So E dot is 0, and so E is a constant, and that's what we saw in the previous slide. So Ty plus y plus is the incoming flux. So we're going to focus attention only on the right-hand side of this thermofield double state. And so the incoming flux, which is coming from the CFT bath into the black hole, is the incoming energy flux is dictated by Ty plus y plus. The outgoing energy flux from the black hole to the bath is dictated by Ty minus y minus. And so that is our Hawking radiation. Okay, so I'll say a little bit about islands and page curves in equilibrium. In this equilibrium scenario, when we expect that in thermal equilibrium, we expect that nothing evolves with time because everything is in equilibrium. But strictly speaking, that's not true, because even though two systems may be in thermal equilibrium, or a system may be in thermal equilibrium, it may not be in entropy equilibrium. And that's basically what we see here. So there's a few things about JT gravity. First is that the entropy of the black hole state is basically given by the value of the dilaton at the horizon. And that's the realization of the Bekenstein-Hawking formula for 2D gravity. Now, there is this recipe or the prescription for the generalized entropy, which I'm not going to make any attempt to derive. I'm just going to state it and then use it and then see its consequences. So the generalized entropy, which is basically what is at the heart of resolving this the information loss paradox and reproducing the right page curve. The generalized entropy is the generalized entropy of some region in this geometry is given by the extremal value of this phi, the dilaton, plus the CFT contribution to the entropy of the region D of interest extremized. And so one takes the extremal value of this thing and that this combination, and that defines the generalized entropy. So just to make this clear, if that's not very clear, so in the case of this two-sided black hole setup, we can imagine asking what is the entropy of the Hawking radiation. That would mean that we are interested in computing the von Neumann entropy, which in CFT language is the entanglement entropy of the Hawking radiation, which means that we go to the CFT bath and look at the entire spatial section of the CFT, which I call capital R, R standing for radiation. And we want to compute the entanglement entropy of this region R, the dotted lines. Now, if we are in the thermofield double state, as we are here, so of course we can view the black hole as a thermal state, but we can also view it in the thermofield double language, in which case one is viewed. So we are taking the left and the right sides of this picture, and it's an entangled, we have an entangled thermofield double state, and that state is a pure state. So when we compute the entanglement entropy of the spatial region, the CFT bath regions, that is equal to the von Neumann entropy or the entanglement entropy of this region D, which connects these two boundary points and which passes through the ADS2 bulk. And that's because the total state is a pure state. So the entanglement entropy of a subsystem in the pure state is equal to the entanglement entropy of the complement. So S of R is the same as S of D. Now, the point is that of this formula, of this generalized entropy formula, is that there are actually two possible contributions to this entanglement entropy. One is one does a straight CFT calculation and just computes within CFT, because we have CFT propagating in here. So we just use our standard Cardy-Calabresi formula adapted to the ADS2 background. So we just have CFT in ADS2 background, and the result, because it's a conformal field theory, is going to be dictated exactly by the usual result for the entanglement entropy of an interval in 2D CFT. The only thing that will potentially change is some contribution from conformal factors at the endpoints, but that's not a major contribution in this example. So that's one example, and this is what we call the no island contribution. But there is another contribution that can appear, which is the so-called island contribution, in which actually one considers the combination of the dilaton and the CFT contribution to the entanglement entropy, and one assumes that there are disconnected regions that can contribute from behind the bulk. So this D is actually a disconnected domain, and on the left side it ends on this quantum extremal surface, on the right side it ends on its mirror image. And so one computes the entanglement entropy of this D, of this little interval D in CFT, adds to it the value of the dilatons at these 2 points, and then one extremizes. Okay, so extremizes with respect to the location of this particular point. Okay, so when one does that procedure, one sees that there is a no island entropy, which is from the left-hand figure, and that gives us C/3 log cosh 2 pi t over beta. That is kind of the result that one gets usually just from looking at the entanglement entropy in the thermofield double state. And then from the island contribution, one sees that basically because when one does the extremization, the quantum extremal surface sits very close to the horizon. This point sits very close to the horizon. And so one ends up evaluating the dilaton very close to the horizon, and one effectively gets just twice black hole entropy at that temperature, plus some small constant corrections, which I haven't bothered to write down. Okay, so the island contribution in this case gives us the black hole entropy 2 times because we have the thermofield double state, and the no island gives us a linear growth in time at late times because log of cosine cos t goes like t at late times. So now we have basically the resolution of the original version of the information loss paradox. If we hadn't included the island, the entanglement entropy in Hawking radiation would have continued to rise linearly forever. But now if you consider this combination and pick out the saddle with the lowest entropy, then you know that you're going to switch saddles from the no island to the island saddle, and the entropy will saturate, and the saturation will occur at this crossover time, which is the page time. So of course we must remember that in this case, the entropy of this black hole does not go to 0 because we have boundary conditions where there's a CFT bath outside, which is held at a fixed temperature beta inverse. And so basically the final saturation temperature is, the saturation value of the entropy is precisely given by twice the Bekenstein-Hawking entropy of this black hole at that temperature. But there is a turnaround, and that's the key point, and that turnaround point is the page curve, and that's what the island contribution gets for us. Okay, any questions at this stage?
Not for me.
Okay.
Yeah, sorry,
Hi.
go John.
No. I was just saying not for me. No questions.
Okay.
Oh, I have a question. Question is, the island entropy is it always just a fixed value at 2H?
No, it's a very good point. So in the example that we will see where you actually have dynamics in the system, that's not the case. So indeed, the reason here it comes out to be a fixed value is because, at the end of the day, this is a system that is at equilibrium with the CFT bath at late times. And so the value is, so the final value of the entropy is a constant. But indeed, this island entropy, island contribution to the entropy can change with time, and it will actually.
Okay. There's a question in the chat. I don't know if you can see it.
Let me see. Probably will have to. Yeah. Do I have to go out of the share?
No, the chat is just at the bottom there. You should be able to see the. I can read it to you. It's from Nahal. It says, I might be mistaken about something, but it essentially looks like you're saying that S of R UI will follow the page curve, where R is the radiation and I is the island. But wasn't the paradox to explain why S of R follows the page curves? The bags of gold problem.
The key point is that indeed, so the point is that R union I is actually contained in R. So this is one of the, this is the non-trivial. So the point is that there is something called coarse-grained entropy and a fine-grained entropy. And there's a coarse-grained entropy R union I, which is actually contained completely in the fine-grained entropy of R. So what we are computing here is not the entanglement entropy of R. We are computing basically the fine-grained entropy of R, which knows about I. Okay, so again, to make this clear, this is not just the entanglement entropy. This is the fine-grained entropy, which has information about I behind it. Does that answer the question? It's the no island, the no island contribution is basically the naive entropy, and the generalized entropy does much more than that.
So I have a question. So in this language, is there a way to see it from the RT prescription? So what would that mean?
Yeah, so in the RT, so I didn't have a slide on that because I was, I had too many slides. I wrote up the talk and I found too many slides. But in the RT prescription, so here, of course, because it's 2D, the notion of a surface, well, you don't have a surface, it's just a point. So you can think about this as an RT prescription. But there is a more direct way to the RT prescription where you imagine. So if you think about what this system really is, So hang on, I want to go back to full screen view here. Yeah. Okay, so if you think about what the so what the system is here, so we have a CFT bath, which is Minkowski, CFT2 and Minkowski, and it has a boundary. And at that boundary, we are joining it to an ADS2. So the ADS2 can also be viewed as the holographic description of a quantum mechanical degrees of freedom living on the boundary of this CFT2. So we imagine that the same system can be replaced by a CFT2 on a line with a boundary, okay? And then you can imagine asking what if this CFT2 with a boundary has a holographic dual, okay? Then that holographic dual geometry would be an ADS3, and the boundary, its holographic dual of the boundary is a kind of what people call the end of the world brane. I wish I could write, but I don't have the tools to write on this transparent on the slides right now. So, but what you have is the on the bulk is the ADS3 and an end of the world brane. And then when you're computing entanglement entropies or the entropy of the Hawking radiation, you basically have a contribution from a Ryu-Takanagi surface that ends on this end of the world brane. And that ending on the end of the world brane is basically what the quantum extremal surface represents.
But there's it's actually, but is the surface is breaking? Is there a breakdown?
The surface doesn't break, it ends on this brane. So the ending on this end of the world brane, which is where you can imagine the black hole or behind the horizon degrees of freedom are basically characterized by this location of the quantum extremal surface.
Okay.
Yeah, so indeed, there is a, I think probably I misunderstood your second question. Indeed, there is a kind of transition between the connected to disconnected route.
Yeah, because as you grow forward in time, there is the RT prescription, the RT surface can break, right? And then
yeah, exactly.
So
that's exactly what
entropy saturates.
Yes.
Yeah. So in a way, the island is so you're when that breakdown is happening, you're compensating that for the island, right? By
yes.
adding this island contribution.
Yeah.
And
so that exactly is what's going on. But of course, there is a much more constructive way to view this, which is to actually do the replica calculation. And in the replica calculation, you do see that these saddles emerge. So you don't need the Ryu-Takanagi prescription separately. You could have deduced just within 2D gravity, JT gravity.
Okay. Thank you.
Right. So that kind of completes the first part of my talk. And the second part, I'm going to talk kind of about what we did. And so it goes back a little bit to precisely what Jeff was asking. So one of the questions we wanted to ask is what happens to these quantum extremal surfaces when there is time evolution. In particular, what happens to these page curves when we are looking at evaporating black holes. And in particular, we wanted to understand the special case of the shock wave matter being thrown into the black hole, which then manifests itself as a shock wave, and then the black hole is excited and then it relaxes. So I should mention that very similar situations have been considered in the literature among some of the papers that I've already referred to, but they use different, they are studying kind of different situations, which I'm probably happy to talk about later. But what we are doing is basically what in CFT would be called a local quench. So I just included this transparency or this slide for some kind of completeness here. So in a conformal field theory, you can imagine creating a local disturbance. So imagine you have a CFT in a thermal state, and you can imagine introducing a local disturbance at some time t equals t naught by inserting some operator, ideally a primary, with some conformal dimension delta O. And if you choose the insertion points of this operator just right, then you can get what is called a finite width local quench. The finite width just refers to the point that you've created an excitation which has a finite amount of energy, which is localized in a small interval. The width of this interval can typically be controlled in this picture by taking the insertion of the operator. So if we imagine that we are starting with a density matrix, the density matrix has both a bra and a ket. So if you want to construct a state which corresponds to a local excitation, you need to insert two of the primary operators, an O and an O dagger, one for the bra and one for the ket. So that's basically what one is doing here. And one separates these two insertions slightly in imaginary time by an amount epsilon, and that serves to regulate the amount of energy that you have in the excitation. And so one can look at this local quench or local excitation, and one can evolve the system in time. And what happens when does this kind of local quench is at time t equals 0, you have a lump of energy. You can compute that quite explicitly in CFT. The expectation value of a stress tensor in this kind of density matrix is completely fixed by conformal invariance. So you can compute, so it corresponds to a pulse of height 1 at time t equals 0. At time t greater than 0, the pulse splits into two pulses, each of height 0.5, moving in opposite directions, left moving and right moving. So this is what we mean by a local quench. And these two pulses, they will basically look like shock waves when these pulses enter the gravitating region of the background that we talked about earlier. So in the limit that this width, the epsilon, goes to 0, the stress tensor, or the left moving and the right moving stress tensors, basically look like the thermal expectation value plus a piece which is exactly proportional to a delta function. So you've got two delta function pulses moving, left moving and right moving. The strength of the pulses is dictated by the energy that we have put into the shock. That energy is given by the dimension of the conformal primary divided by the width, epsilon. So we have a completely precise description of what we mean by a finite energy pulse, a local excitation in the CFT. If we were doing CFT entanglement entropy calculations, what we would find is that the left and right moving pulses, since they're entangled, they are basically like qubits. So they're two entangled qubits, and one of them, one of these pulses, if it enters the interval of your interest, whose entanglement entropy you might be computing, you will find that as soon as the pulse enters the interval, the entanglement entropy jumps. And the jump is controlled by the intrinsic entropy of the operator that is used to build this excitation, which is typically called this quantum dimension of the operator. So this is basically the scenario we are thinking of. So we are imagining that in the CFT bath, we do a local quench. We have a left moving and a right moving pulse. The right moving pulse remains in the radiation bath. The left moving pulse gets into the ADS geometry and falls into the black hole. The energy of this shock wave that is sent into this black hole is delta O over divided by epsilon. We will call it E shock. There is an intrinsic dimension to this pulse, which we will call, which is controlled by the quantum dimension. We will call S shock. Neither of these two quantities need to be specified. They can be treated as dials. So what we want to understand is what is the back-reacted background after this shock wave has been sent into the bath. And I should mention that we are doing this symmetrically on both the left and the right. We need not have done that, but that's actually an even more interesting question. What we are doing here for simplicity is imagining that this quench is done at the same time on both the left and the right of the thermofield double. So before the shock wave is sent in, both the bath and the black hole are in thermal equilibrium, as I've mentioned. The bath and the stress tensors are given by the thermal normal ordered expectation values. And as I mentioned, you can compute the ADM mass of the ADS black hole. The ADM mass is given just by the Schwartzian. So if you're going to transform from Poincare coordinates to the black hole patch, the coordinate transformation has a Schwartzian associated to it. And that Schwartzian gives you precisely this result. It's the same Schwartzian which also gives you the thermal expectation value of the stress tensor. So the energy of this black hole, or the mass of the black hole, goes like temperature squared times this overall constant, 1 over g Newton. So when we throw the shock wave into the bath at time t equals t naught, the black hole gets excited, and it gets excited to a new, we will call this a new effective temperature, because basically the black hole energy is now shifted. It is E beta, which was given by this, plus E shock. And we can use the previous formula that we had to define for us a new beta tilde. Okay, so there will be a higher temperature associated to this excited black hole, which is beta tilde inverse, which is completely determined in terms of E beta and E shock. Okay, so now what's happening after the shock is that we have the CFT bath at temperature beta inverse, okay? The outside, the Minkowski part of this glued together geometry, the CFT bath is still at temperature beta inverse. So the incoming flux of energy, T y plus y plus, is still given by the old thermal expectation value. The outgoing flux, however, changes. And we can imagine that we don't know exactly how it changes, but we know that it has to change by a Schwarzian. And that Schwarzian will be associated to a function f of t associated to the reparametrization of this boundary time coordinate. Now, a very simple way to understand this reparametrization is to go back to what I said in the previous slide. Imagine that at time t equals t naught, when you threw this shockwave into the black hole, and you imagine the black hole is now described by a higher temperature state at beta tilde inverse. That means that you would say that if that were true, then the expectation value of the outgoing flux should be given by the thermal expectation value of this Ty minus y minus evaluated at the temperature beta tilde inverse. And so that would give you a different flux. It would give you pi c over 12 beta tilde squared. And these two fluxes wouldn't be equal, and so there wouldn't be a cancellation. And therefore, the black hole state would start relaxing. And then the system would become time dependent, and that's why we need to have a time dependent f of t here. Okay, so our task is to basically determine what this f of t is if we want to find out what this relaxing geometry is or the relaxing background is. Is there any question? Because this is kind of an important point at this stage. Okay. I'm assuming that this was fairly clear, that immediately after excitation, the left moving incoming and outgoing fluxes are not equal at the boundary. And so what remains to be done is to determine this f of t, which is this reparametrization. This reparametrization, essentially, it connects the new background to the Poincare patch, and it tells us exactly what this coordinate redefinition is. Once we know what this coordinate redefinition is, to go back from the excited background to the Poincare patch, we have full information about this background. So the outgoing stress tensor takes this form in terms of the Schwarzian, and then we can write the energy flux equation, the energy balance equation at the boundary. So here's the boundary a kind of schematic depiction of the boundary, ADS2 boundary between the ADS and the CFT bath. Shockwave sent in, something happens here, and there is non-equilibrium. So E dot is now given by the difference of these two fluxes. What is very interesting immediately is that the ADM mass of the geometry is also given by the same Schwarzian. And therefore, on the right-hand side of this energy flux equation, we can say that E dot is pi c over 12 beta squared minus a constant times the ADM mass. And so we have a simple first-order differential equation for E as a function of time that, of course, has an immediate solution in terms of exponentials. The constant K here is important. It's written in terms of Newton's constant C and the value of the dilaton, this particular combination. This K has to be small because this is what governs the coupling of the matter fields to the gravity sector. And so in the semiclassical limit, this K has to be small compared to 1. So like I said, this equation, the energy flux equation, has an exact solution. And what it tells us is that the energy, the black hole state gets excited, and then the energy decays exponentially. What is, as a function of time, what is nice, and what we will see at this point, this is not, this statement doesn't have too much content in it, but as we move along, we'll see that there's actually physical content in this formula. We can say that the energy can be written as pi phi over 4 g Newton divided by an effective temperature, times an effective temperature squared. And this beta effective, or this effective temperature, is this particular combination of the original temperature, the shockwave energy, and the original energy of the black hole times this exponential decay. So what this is saying is that we've identified something that can potentially be an effective temperature that governs the decay of the excited black hole from this new high temperature state back to its original equilibrium state by emission of Hawking radiation. And here we are assuming that K is small compared to 1, so the relaxation by Hawking radiation occurs slowly. It occurs on time scales of order K inverse, which is much bigger than 1. Okay, so the main problem in all of this is basically to figure out, to understand what the background is and to understand the details of what the page curves, etc. are, we need to know what this what this function f of t is. And what we are seeing here is that, so we know that the energy of, we know that the mass, the ADM mass, I've already said this a few times, we know that the ADM mass of the background or the energy is given by the Schwarzian. And now we know what the time dependence of the energy is. It's this exponential function of time. So we just need to solve this differential equation. Schwarzian of f of t equals this 1 over beta squared effective, which is just an exponential function of time. And because this is a Schwarzian, the solution is determined up to SL2R transformations. So whatever fiducial solution that we might find, we will have to fix it or fix these integration constants. There are 3 integration constants here, and they will get fixed by matching this f of t that we get, the particular solution. We will get these integration constants by matching to the values of f of t, which were dictated by the thermal black hole coordinates at times t equals t naught. So we have to match f of t, f prime of t, and f double prime of t at t equals t naught. So the nice thing is that this differential equation can be solved, and it has a solution in terms of ratios of Bessel functions. Okay, these special Bessel functions. And the index of the Bessel function is proportional to the temperature, 2 pi over beta k. It's important that this particular combination 1 over beta k enters. And the argument of the Bessel function, it depends exponentially on time, e to the minus kt. Okay, so Bessel's functions are nice, but they're often quite opaque. So what do we learn from these solutions? First, we learn that if you look at the late time limit of these exact solutions, at late times, the Bessel function, so f hat of t, by the way, is what is basically the minimal solution, or what I call the fiducial solution. The actual coordinate transformation f of t is determined by a f hat plus b by c f hat plus d. A, b, c, d are all determined in terms of, Bessel's functions evaluated at t equals t naught. So it's not important what a, b, c, and d. So what one finds is that late times f hat of t is given by z to the minus 2 nu, where z was the argument of the Bessel's function, and that actually translates to e to the 2 pi t over beta, which is basically saying that at late times, the behavior is consistent with what one would expect for a system at temperature beta inverse, because system is relaxing back to its original temperature, and you recover the periodicity in imaginary time associated to t goes to t plus I beta. What about early and intermediate times? And this is opaque generally when one is dealing with these Bessel's functions. There's a very useful limit which we consider, which is the limit where nu is much bigger than 1 for all times. So nu much bigger than 1 is a very natural limit, because we are k small is a semiclassical limit, as I already mentioned. So we can view this nu much bigger than 1 limit as a high temperature limit. So it's the limit in which beta k is much smaller than 1. And so beta is much smaller than k inverse, or t is much smaller than k. Temperature is much bigger than k. So it's a high temperature limit. So a nice thing about this large nu or high temperature limit is that if you look at the Bessel functions, they have integral representations. You can see that the integral representations of the Bessel's functions are dominated by a saddle point at large nu. A nice exercise to do. And in this saddle point, one discovers a very nice and suggestive form for this function f hat. In fact, f hat looks like it's almost quasi-thermal. So if you compare f hat, the thermal behavior is e to the 2 pi t over beta, but all along the temporal evolution, f hat looks like integral of t dt prime over beta effective of t prime. So in fact, in this limit, we can describe the relaxation of the black hole as some kind of quasi-thermal process. And at each time step or each time scale, we can identify an effective temperature. So it's some kind of adiabatic relaxation of the black hole, which we can describe precisely in this limit. Okay, so this turns out to be useful because we can now do many things basically analytically. So the function f of t, this is just for information, in this limit can also be completely determined. So that means that we have completely parameterized this, this diffeomorphism that takes the deformed black geometry after the shock wave is thrown in, and this is the relationship between the coordinate of the boundary time in t is the physical time in this deformed geometry, and f of t is basically what we would call Poincare time. So f of t determines the relationship between Poincare time and the physical time in this deformed boundary. So we can look at the details of what these functions do, etc. But there's of course a very simple picture. First, that if you look at what happens to the black hole when you throw in this shock wave, as expected, when you look at these formulae, you can conclude that the horizon of the black hole moves outwards, as you might expect, because the temperature has increased, and this horizon remains, of course, exactly where it is. And this, the value, the location of this new horizon, its exact location with respect to the location of the old horizon, which is given by x minus equals beta over pi, the new location is determined not just by the beta tilde, which is the temperature after the shock wave was thrown in, but also depends upon when you throw in the shock wave. So there are different dials in the system, T0 when you throw in the shock wave, beta tilde, which measures how much energy is carried by the shock wave. All of these determine how big the horizon of this new black hole is. The dilaton is the main ingredient, and its solution is kind of a bit messy, but one can actually show that this particular example that we are looking at, we can actually solve for it exactly. So once we know this function f, we know the dilaton as well. So I don't want to write it down, it's not very useful. But now that we've got all information about this geometry, the function f of t, it allows us to determine what the dilaton is. We can now compute what the black hole entropy is. So the evaporating black hole entropy is given just by the value of the dilaton at the horizon. If you do this exercise, you discover that the black hole entropy is a function of time, and it is determined in terms of this function f hat, which we determined earlier. This is an exact formula. And then if you take the large new high temperature adiabatic regime, you find that the black hole temperature is given precisely by what you would expect the thermal entropy for the black hole to be, except now beta is replaced by beta effective of T. So the black hole relaxes all through the way exactly as if it was at some temperature given by beta effective inverse as a function of time. So now we want to kind of mimic the calculation of the entropy of the Hawking radiation that we did in the equilibrium case. So we're thinking about this deformed geometry, shock wave thrown in, horizon shifts. Now we have the thermofield double description of that. Want to compute the entropy of entanglement of this Hawking radiation. So again, there are two contributions. There is the no island contribution, in which we have this domain D, which intersects the shock wave. So when you compute the entanglement entropy, it's exactly like doing a CFT entanglement entropy calculation. So it's given exactly by Cardy-Calabresi type formulae. You just have to adapt them to the coordinate system associated to this ADS2 black hole, which is admittedly a little bit tricky because the coordinates, in order to do this explicitly, you have to map your deformed coordinate system back to the Poincare coordinate system, write down the answers in the Poincare patch, and then transform them into this new. So I haven't done all that, but basically the idea is that there is a no island contribution, which is Cardy-Calabresi, plus some contribution from the intrinsic entropy carried by the shock waves. This is controlled by the quantum dimension of the operator that you use to produce the excitation. So there's these two contributions. And then we can analyze what this no island entropy does as a function of time. So the detailed solutions we don't need to look at. Here is basically the summary of what happens when you look at the no island contribution to the entanglement entropy of the Hawking radiation. So the no island contribution, I basically, you can ignore the first two lines of this slide. The no island contribution comes in three distinct time scales. Early time scales, when actually the no island contribution behaves exactly like the thermal, like the no island contribution for the thermal case at temperature beta inverse. Okay, plus there is a contribution from the shock, intrinsic shock entropy. Then there is an intermediate time scale, which is an interesting time scale, which is where the effect of the shock, the excited state kicks in. And what you find is that the no island contribution, it still grows linearly with time, but the slope, the velocity of the growth of the entanglement as a function of time now increases. Increases because we have a piece that looks like pi c over 3 beta tilde, and we know that the new temperature immediately after the shock wave is thrown in is higher than the old temperature. So the slope of increase here is bigger than it was before. So indeed, the growth rate speeds up after the shock wave is thrown in. Then you have a late time regime when the system is relaxing. And there again, when you compute the no island contribution, quite non-trivially, you see that the no island contribution again looks like it's going back to what it was before. So it's growing linearly with time, but with this slope dictated by the temperature of the original state. Okay, so we have these three distinct states for the no island contribution. You can do the same thing for the island contribution. So now we have on both sides these contributions, which are these disconnected intervals. And now actually there are interesting situations to consider. And there is when this quantum extremal surface could either occur in front of the shock wave, which means that the shock wave hasn't hit it yet, or it could occur behind the shock wave. So it could occur either here or there. Both are possible. So we have to consider both these cases. And you can see that there is now richer structure because there are more kinds of saddle points that can appear. So we do the calculation and we find that for the quantum extremal surface in front of the shock wave, for this particular case, you can see that there are again three distinct time scales. There's an early time scale when the quantum, when the value of the generalized entropy is basically given just by twice the black hole entropy. Again, this is an approximation because there's a small piece that can be time dependent, but it's small and remains small for all times. So at early times, it's given by twice the black hole entropy, but the initial black hole entropy plus a shock wave contribution, because the shock wave is actually passing through this interval D. At intermediate time scales, again, you find twice the black hole entropy, the original black hole entropy, plus the shock wave contribution. But now you have a growth rate of this. So note that the quantum extremal surface island contribution also has a piece which increases linearly with time at intermediate time scales, with a velocity or slope which is the same as the no island contribution which we saw on the previous page. Then at late times, this quantum extremal surface in front of the shock wave, that gives a contribution to the entropy that goes like, twice the original black hole entropy plus a linearly growing bit, which again, whose slope is dictated by the old temperature. So these are basically the possible behaviors of the quantum extremal surface coming in front of the shock wave. And now finally, we have the quantum extremal surface behind the shock wave. And this is actually the most interesting because this is the one that dominates at arbitrarily late times. But in between, you actually have a competition between these three different contributions or these three different saddles. So the quantum extremal surface behind the shock wave, the story is actually quite interesting, and I'll summarize it in the second to last slide. That when you compute the entropy associated to this, you will find first that the quantum extremal surface tends to always be behind the new horizon, which is actually interesting because in all the examples that have been studied to date, the locations of the quantum extremal surfaces are actually always a little bit outside the horizon. So this was always a bit puzzling, and we were wondering whether there is any situation where the QES can be behind the horizon. So indeed, in this non-equilibrium situation, it turns out the QES is behind the horizon. but it is sufficiently close to the horizon that if you look at its time evolution, it's basically dictated by, or the value of the entropy, it's basically dictated by the value of the black hole entropy, okay, associated to the given time, the given boundary time t. Okay, so there's something about scrambling time which I won't talk about, but here is basically the picture that summarizes what happens to the quantum extremal surfaces. Okay, so you can ignore the first two bullet points in this slide. So here is depicted the behavior as a function of time in green and in blue, the behavior as a function of time of the quantum extremal surface which occurs in front of the shock wave. So here as a function of time, this is the boundary point, sorry, this is the boundary point or the boundary time that we are interested in. And as this boundary time increases, you can see that the associated quantum extremal surface gets closer and closer to the original black hole horizon. The boundary time crosses the shock wave point of entry, and we've got the blue dot here. The associated quantum extremal surface actually comes arbitrarily close to the original black hole horizon and more or less freezes at a particular value of this light cone coordinate. And then as you keep increasing the boundary time, suddenly the quantum extremal surface pops up behind the shock wave. And so that's basically what's depicted here, is that you've got this red saddle point, sorry, the red boundary point, and the associated quantum extremal surface saddle point is now behind the shock wave, but also behind the horizon. And what you cannot see in this figure is that as a function of time, as you evolve forward, eventually as the black hole approaches equilibrium, this quantum extremal surface migrates outside the horizon. And the system begins to look exactly as it was in equilibrium, way before anything was sent in. So that's the behavior of these quantum extremal surfaces in this non-equilibrium problem. And once one has all these quantum extremal surfaces, because there are multiple saddles, as a function of time, there are multiple scenarios that can take place, and which scenarios realized depends upon the dials you have in the problem. So the different dials include the insertion time t0 relative to the original page time, and the value of the shockwave energy and the shockwave entropy. So these are dials that you can freely twist. Generally, the basic idea is that once you throw in a shockwave, because the shockwave consists of two pulses, one's going into the radiation bath, into the CFT bath, and the other going into the black hole, the two are entangled. So when the shockwave enters the black hole region, it increases the entanglement between the black hole and the radiation bath. So that means that it's going to increase the velocity of the growth of the entanglement. And so it hastens the page time. But there is another effect, which is that since the shockwave carries energy, it heats up the black hole. And so it raises the black hole entropy. And that has the effect of delaying the page time. So you have these two kinds of competitions going on. And so here are these two kinds of kind of generic scenarios for which we have plots, but one can think of others. So here is on the left, we have basically what's happening here is the shockwave is thrown in before the page time of the original page time of the black hole. So here we have the no island contribution to the entropy of the original black hole growing linearly. Shockwave is inserted, and then you have some small jump here because the shockwave has an intrinsic entropy associated to it. And then because the shockwave has increased the entanglement, you see that the slope of this growth is faster. And then eventually there is a crossover point where this no island entropy is beaten, or in fact its entropy is higher than the island entropy, and the red contribution here corresponds to the quantum extremal surface after the shockwave or behind the shockwave. And so there's an exchange, and then you can see that the entropy associated to this quantum extremal surface is also relaxing as a function of time. Eventually it will relax to equilibrium, the late time equilibrium. So here you see the time dependence of the whole process. And then here we have another example where the shockwave is thrown in after the after the page time of the original black hole. So shockwave thrown in, and here we have the island saddle of the original black hole in green. The shockwave is thrown in, and then we have a transition to the quantum extremal surface, okay, which is before the horizon, before the shockwave. So we get a transition here to this quantum extremal surface that appears before the shockwave, and then a final transition to the quantum extremal surface, which appears after the shockwave, and then finally relaxation to equilibrium. So it's a complicated rearrangement of the entanglement structure in the presence of the shockwave, and so the entanglement structure in the presence of these shockwaves and the time dependence is generally quite rich and complex. You can of course think about multiple shockwaves, which is quite interesting as well. And the analysis of what we've done actually here was for a finite temperature black hole being heated up and then watching how its entanglement and how the entanglement entropy of the Hawking radiation relaxes. We can also do this for the extremal ADS2, zero temperature ADS2 with a shockwave thrown in and heating it up to form a black hole, which eventually evaporates. So the analysis can be repeated in this example, which is kind of more interesting. There are open questions which kind of currently in progress, which are more refined questions, which have to do with exactly the details of this island proposal, which is how the island is actually contained in the late time Hawking modes. So exactly how precise question relates to how the late time Hawking modes are entangled with the early time Hawking modes. And finally, exploring this kind of structure or the rearrangement of entanglement structure in the presence of shockwaves in the boundary conformal field theory holographic framework, which is a kind of different representation of the same system where the CFT2 can be realized holographically, and we can try and understand these kinds of phenomena within the framework of holography and shockwaves. So I'm sorry for going over time, but thank you very much for your attention.
Thank you.
Thank you very much.
Thanks, Prem.
Does anyone have any questions?
So I have a question. Prem, in the
Yeah,
I think 2 slides from the end, you had graphs of, yeah, those.
yeah.
One forward.
Forward, yeah.
Yeah, those. On the plot on the right hand side, where's your page time there?
This is the page time.
Okay.
So page time is always associated to the, the transition to the lowest entropy saddle.
Yes. Yes, I see. Okay. So how dependent is, so I have two questions. One is, how dependent are these results on your asymptotics? So you have asymptotically ADS2 here, but you could also have an asymptotically flat background with a slightly different structure for the gravity, not JT gravity, but I'm trying to think what you would call it. Something like Poincare gravity. So the symmetries are not ADS2 symmetries. The symmetries are.
Yeah, the expectation somehow is that if you were discussing the physics of these near extremal black holes, related to higher dimension near extremal black holes, would expect that this captures that fairly universally. And of course, there is a kind of idealization here where we are gluing together the asymptotic Minkowski region as just a pure Minkowski non-dynamical gravity region. But I think the expectation is that making that dynamical will not have a significant impact on this. But that, of course, one needs to have a framework to compute. But that's an expectation, I think.
Mm-hmm. Okay, I think that answers.
I mean, in a sense, the Minkowski asymptotics is just mimicked here by putting in the CFT bath, flat space CFT bath, and switching on transparent boundary conditions at the boundary between the ADS2 and the CFT.
Right. Right. Interesting. Thank you.
Can you also comment on what will happen if you gave the shock only on one of the sides?
Yeah, so I think that's a very interesting situation. So I don't think we have studied this, but something very similar to this has been studied by, I think there is I'm not sure if I referred to them here. Yeah, probably not here. So there's a paper by Almheri, Engelhardt, and co, where they study similar situation. So we have completely ignored that. We have completely ignored any kind of entanglement or interaction between the two boundaries, and that's a very interesting thing to consider, how sending in a shock wave from one boundary to another destroys the entanglement structure. So that's similar in some kind of spirit to what people did with the Schenker-Stanford story, where you've got two boundaries and you send in a shock wave from one boundary to the other, and then you study how scrambling, how this results in scrambling and destruction of the entanglement structure. So I think that's kind of very interesting, certainly. But I think the full dynamics of this, in the way that we have analyzed, has not been completely fleshed out. That's my understanding.
Okay.
Any other questions?
Nothing from me, no. That was great.
Okay. Well, thank you very much, Prem, for the talk.
Thank you.
I'll see everyone next week.
Thank you.